Every time you generate an AI image, or ask a chatbot to write some code, or honestly just scroll through an algorithmically curated feed, you're actually tapping into a massive global energy drain. High-performance AI is incredibly hungry, and right now our data centers are devouring power at a scale that is simply unsustainable. But what if I told you we could slash the energy cost of computing, not by 10%, not by 20, but by 100 times? What if the solution to our digital energy crisis requires us to stop building traditional computers and start looking at biology?
Welcome back to The Explainer. Today, we're going on a pretty wild journey. We're going to start at the macro level with the energy crisis of modern computing, and we're going to drill all the way down into nanoscale materials science. As you'll see, engineers are literally reinventing the microchip from the ground up.
Okay, let's dive into this. Here is our roadmap for today. We'll start with the AI energy crisis, then move to brain-inspired computing, look at how hafnium oxide RRAM works, discuss programming synapses, and finally, look at the DNA-powered Memristor revolution.
Starting off with Section 1, the AI energy crisis.
To really understand the solution here, we first have to establish the stakes. The AI workloads running quietly in the background of our apps and businesses are incredibly demanding. And our current hardware? Well, it's struggling with something called the memory wall. See, traditional silicon chips are highly inefficient because they physically separate the memory units, where data is stored, from the processing units, where the actual math happens. Imagine you're trying to cook dinner, but your refrigerator is in a completely different building than your stove. You'd waste an immense amount of time and energy just constantly shuffling ingredients back and forth, right? Well, that is exactly what traditional computing does with data. And as AI workloads explode, this constant shuffling is absolutely devouring power.
Let's move to Section 2 and see how this builds. Brain-inspired neuromorphic computing.
So to fix this memory wall, engineers realized they needed a totally different blueprint. And as it turns out, the most energy-efficient computer in the known universe is sitting right inside your skull. Neuromorphic computing is exactly what it sounds like. It is computing architecture engineered to mimic the adaptable behavior of biological neural networks, such as spiking neurons and learning synapses. So instead of rigid lines of code processed sequentially, we're talking about physical hardware that mimics the way a real biological brain adapts, learns, and holds information.
The real game changer of this approach is in-memory computing. If you contrast the cold, inefficient separation of standard silicon with biology, it's night and day. In a brain, your synapses act as both the memory and the processor. The data is processed exactly where it's stored. By co-locating memory and processing right there on a microchip, we completely bypass that energy-wasting trip back and forth. It saves massive amounts of power.
Which brings us right into Section 3, how hafnium oxide RAM works.
Now you might be wondering, how do we actually build a biological synapse out of metal and glass? Well, now what's really interesting about this layout is the comparison here. You'll see a standard 1-resistor device on the left and a 1-transistor 1-resistor layout, or 1T1R, on the right. When we program these memory cells, the current spikes really rapidly, which could totally fry the device. The 1T1R layout is absolutely brilliant because that transistor acts as a gatekeeper. It limits the current, a process called current compliance, so we can safely program the memory into a low-resistance state without literally burning it out.
But let's look at what's actually happening inside that resistor. It's all about these set and reset transitions. Step 1, we apply a voltage. This causes oxygen atoms in the hafnium oxide to move around, leaving behind these little gaps, or oxygen vacancies. Step 2, these vacancies link up to form a microscopic conductive filament right between the top and bottom electrodes. This is our low-resistance state, and it acts exactly like a biological synapse strengthening a connection. Then for Step 3, to break the connection, the high-resistance state, we simply reverse the voltage, which breaks the filament.
I know, if we look at this under an electron microscope, it honestly looks like an incredibly tiny, incredibly complicated layer cake. But this dense material science is highly intentional. Engineers use what they call scavenging metal layers, like titanium or hafnium, sandwiched between the main hafnium oxide layer and the titanium nitride electrodes. This scavenging layer actually oxidizes by pulling oxygen from the hafnium oxide, creating an asymmetrical oxygen vacancy profile. That little chemical trick dramatically lowers the voltage needed to form the filament in the first place, saving us even more power.
All right, let's move to Section 4, programming artificial synapses. So now that we understand the physical structure, our little nanoscale layer cake, how do we actually teach it? Well, the crucial point is that a memristor remembers its past. Because it's a physical filament, we can read its resistance state using a very low voltage, one that won't accidentally trigger a change. Basically, we can check its memory without destroying its memory.
And because we can precisely control that transistor we talked about earlier, these devices aren't just rigid binary zeros and ones. By using techniques like incremental step program verify algorithms, or by sending a train of weak voltage pulses, we can program these hafnium oxide devices into hundreds of different resistance levels. We call this analog conductance modulation. It perfectly simulates the gradual analog learning curve of a real biological synapse over time. We aren't just storing static data anymore, we are actually updating weights in a neural network, right there on the physical hardware.
Actually, it goes even deeper than that. Some engineers are deliberately building what we call volatile memristors. By using materials like silver nanodots and solid electrolytes, they create conductive filaments that naturally self-dissolve once the voltage drops. Now, you might be asking, why on earth would we want a computer memory that forgets? Well, because real brains forget. This messy short-term relaxation dynamic allows the hardware to emulate biological phenomena like pulse-paired facilitation, where repeated rapid stimuli create a cumulative, temporary strengthening of a connection. It's literally mimicking the actual timing mechanisms of biology.
And finally, Section 5, the DNA-powered Memristor revolution.
If brain-inspired computing is the goal, why stop at just mimicking biology with metal? And this brilliantly illustrates the next frontier. Researchers at Penn State University recently unveiled a biohybrid device that pairs a crystalline perovskite semiconductor, which is the kind of stuff you usually find in solar cells, with custom synthesized human DNA sequences. No way, right? But by combining these materials, they created an entirely new form of memristor that retains clues about its past electrical experience. And the result of this unconventional architecture, a projected 100 times reduction in computing energy use.
The core takeaway here is just monumental. For decades, the tech industry has relied on simply making standard silicon transistors smaller and smaller and smaller to get performance gains, but we've essentially maxed out that approach. By abandoning conventional silicon for biological materials, like DNA, and embracing unconventional computing architectures, like neuromorphic memristors, we finally have a viable path to sustainable, next-generation AI.
We are crossing a truly fascinating threshold where the line between computer science and biology is completely blurring. We've seen how mimicking a biological synapse can save massive amounts of power, and how injecting actual synthetic DNA into a microchip might just solve our AI energy crisis. But it leaves us with a pretty provocative thought to ponder. If our computers start relying on human DNA to form memories, are we still building machines, or are we beginning to grow them? Thank you so much for joining me on this explainer. Keep learning, keep questioning, and I'll see you in the next one.